Okay. So the last time I promised that I'd start by talking about geometric integration methods. And if I could just remind you of the context. When you're trying to understand long-term behavior in planetary systems, you typically have to integrate planetary systems for up to 10 to the 10th or 10 to the 11th orbits. And when you do that, it's important to have an integrator that, it's okay to have an integrator that makes errors in phase, but if it has numerical dissipation, that is, if it has any changes in the systematic changes in the energy or the angular momentum, you'll get disastrously bad behavior. And so you would like to have an integrator that avoids that behavior. Those integrators remarkably have been developed over the last 20 years or so, initially in other contexts. And the general philosophy of a geometric integrator is that it's more important to preserve the geometric properties. Okay, maybe it's better just to leave it off until I need it. No, actually, put it back on. I can put on a blank, put on a black slide. Okay. These are geometric properties with flow and phase space. And to minimize the errors over one step. Again, a typical integrator like the run-and-cutter method is designed to minimize the error in numerical integration over one time step. However, when you're dealing in particular with Hamiltonian systems, you have this complex flow of in phase space of a whole ensemble of systems, and the hope is that if you can make an integrator that keeps some of those properties of the flow, it will behave better than one where you just try to make things as good as possible over one step. So some examples would be, well, a simple one is a time reversible integrator. That is, we know that in a dissipationless system, the motion is reversible. That is, if you integrate forward for some time, reverse all the velocities and integrate back, you should get back to where you started, and so it would be reasonable to have an integrator that does the same thing. It's another possible property would be volume preservation. We know that in a dissipationless dynamical system, Liouville's theorem applies, which says that the flow in phase space conserves phase space volume. If you have a small volume element in phase space, and you follow it, at some later time it will have the same volume. So it would be reasonable to have an integrator that preserve that property. The third possibility is to have what's sometimes called symplecticity. If you recall your Hamiltonian dynamics, the transformation from the phase space position some initial time to some later time is symplectic, or if you like, it's a canonical transformation. I'm not going to try to define what symplectic means, but I'm going to actually replace it by what's not quite equivalent, but close enough, which is the motions derived from the Hamiltonian. Because any motion derived from the Hamiltonian is symplectic. So, again, you can think of this as saying that the real system is a Hamiltonian, so you'd like your integrator to be a Hamiltonian. Okay, so let me describe a specific example. If you'd like more detail, the standard reference is a book by Tyrer et al. Called Geometric Numerical Integration. And just before I describe some typical integrators, as a straw man, I'm going to give you a very bad integrator. So the case I'll look at, again, is a simple Hamiltonian for a particle of unit mass inside a fixed potential. The equations of motion, of course, dp dt is minus grad phi q, and dq dt is p. And if you were trying to integrate those equations in the dumbest possible way over a time step of h, so I want an integrator that will take qp at time t, q prime, p prime at t plus h. I write p prime is p minus h grad phi q, and q prime is q plus hp, and this is called Euler's method. It's a first order method. Well, from the last time you were first order, that means the error after one time step is of order the square of the time step. Again, Euler's method is a terrible method. You should never use it, but I'm putting it there as a straw man. Okay, so if I'd like to derive a better integrator, I'm going to try to make a geometric integrator in which the motion is derived from a Hamiltonian. I take a new Hamiltonian, which is a half p squared plus phi q, and I multiply this by a function that I call delta h of t, where delta h of t is a sum, is h times a sum from minus infinity to infinity delta t minus jh. That is, it's if you like, a picket fence of delta functions equally spaced by h. The reason that this is a natural thing to look at is that if you average this function over any time that's long compared to h, you're going to get unity. Since we're presumably dealing with a short time step, we'd like to preserve the behavior of the system over times long compared to h. It shouldn't be too bad to multiply the potential by any function whose long-term average is unity. So what happens when you integrate these equations of motion with this Hamiltonian? Well, let me start at a time which is slightly before t equals 0, and I'll go to a time which is slightly after t equals 0. There's a delta function here, so dp dt is the gradient of the potential integrated over this delta function. Since the delta function lasts for an arbitrarily short time, the coordinate doesn't change. So you go from p to p1, which is p minus h grad phi with q. I then go from t equals plus epsilon to t equals h minus epsilon. During that time, because the delta function is 0, the momentum doesn't change. So, sorry, let me call this p1. P prime is just the same as p1, but during that time, the coordinate is changing, and so q prime is q plus hp1. Sorry, and here, of course, q doesn't change. By the time we get to h minus epsilon, we've gone for a full time step, so the total integrator is just p prime is p minus h grad q phi, and q prime is q plus h p prime. And you'll notice that the only difference from Euler's method is in this part where Q is incremented by the new momentum instead of the old momentum. So this is called the modified Euler's method. I could just as well have started at t equals plus epsilon. I could have done this step first and then this one. Then I would have had p prime is p minus h grad q prime, grad phi q prime, and q prime is q plus hp. So either of these is modified Euler. There is a slightly more general way to think about these. If I look at this, part of the operator, the integrator, what's happened is you've changed the momentum by a finite increment. You've left the coordinate unchanged. That's exactly what you get if you have a mass and you kick it. So this is called the kick operator. And I'll write this as K sub H. So you can say K sub H maps Q and P onto Q and P minus H grad phi Q. It's a nonlinear operator on the position in phase space. Similarly here, this operator doesn't change the momentum. It just lets the coordinate drift along at constant angular momentum. So I'll write this as I'll call this the drift operator. P sub H maps Q P onto Q plus HP. And each of these operators is symplectic because each is derived from Hamiltonian. Since each one, in particular, the drift operator is derived from the kinetic term of the Hamiltonian. The kick operators are derived from the potential term of the Hamiltonian. So each is derived from a Hamiltonian, so each is symplectic. So if I multiply them together, they're symplectic. And so this operator can be thought of as first applying a kick on the initial position and then applying a drift. This one would be first drift and then kick, where I'm, as usual with operators, you're going from right to left. So since any composition of symplectic operators is still symplectic, I can combine these in more elaborate ways. And so, for example, I can take a half step of a drift, a full step of a kick, and a half step of a drift. And the way that would look in real coordinates is I'd start with Q and P. I define an intermediate step, Q1 half is Q plus a half HP, and P prime is P minus H grad phi, Q1 half, and then Q prime is Q plus a half H. And you won't be surprised to know that this is standard leapfrog. And of course, you could write leapfrog equally well as a half kick, a drift in the middle, and a half kick. Leapfrog has lots of nice properties that make it an integrator that's really the method of choice for a large number of dynamical calculations. As I said, it's symplectic. because it's a composition of symplectic operators. It's time reversible. The nice thing about the operator notation is you can just look at this and you can see that it's symmetric, and that means it's time reversible. It's second order. That is, whereas modified Euler is only a first order method, like ordinary Euler. Leapfrog is second order. You can sort of see that that's natural because any time reversible operator tends to have an even order. Although this is not relevant for planetary integrations, if you're doing a large integration like a globular cluster or worse yet, a cosmological simulation, the other advantage of Leapfrog is that there's no intermediate memory. That is, if you're trying to follow a billion particles, you really prefer not to have to store intermediate steps in an integration, which you do have to do with something like Ramacutta. But if you look at this set of operations, there's no point at which you have to store any more than one set of phase space coordinates. The additional nice property of Leapfrog is that normally when you go from a low order integrator to a higher order integrator, you have to do more work per step. But in fact, suppose you wanted to do n steps of Leapfrog. In the operator notation, you can write this as k. I'll use this one actually. D h over 2 k h d h over 2 to the n. That is n half drift, one full kick, half drift. And I can rewrite this as starting with the half drift step, then full kick step, full drift step, repeat it n times, and then go back half a drift step. And so apart from these one step at the beginning and one step at the end, this is just modified Euler.
Sorry, in the last line of your Leapfrog, where you've got q prime equals q plus a half h p prime, should that first one be q subscript
Sorry,
half?
of course, you're right. That should be q more half. So Leapfrog, in a certain sense, is exactly the same as modified Euler. It's just by adding these extra steps at the beginning and the end, you've managed to up-convert it from first order to second order. So you've gained an order at the expense of negligible extra work. One of the other rather nice, I'll try to keep the kick operator. One of the other remarkable features of these integrators is that you can generalize this sort of point of view. For example, suppose you wanted to have an integrator that was better than second order. You wanted an integrator that was fourth order. Such an integrator was designed by a guy called Foray, and the integrator looks like one step of the integrator is a drift, kick, another drift, another kick, another drift, another kick, and another drift. These coefficients, A, B, and C, have to be chosen just right. Although the actual details don't matter. You make A 1.35120, B minus 0.3512, and C 1.7024. You get a fourth order. Because this formula is symmetric, it's automatically time reversible. Because each of these is symplectic, the integrator is automatically symplectic. And you can generalize this. It's simple to write codes that will generate sixth order, eighth order, 10th order, whatever you want. Although in practice, most of the time people only use second order and fourth order. So let me see if I can give you an example of how they work. So this is a very simple test case, integrating the equations of motion for a particle in a Kepler potential. I'll show three integrations. One is the bad Euler's method that I mentioned at the start. The other is a modified Euler, which is, I guess, a drift kick modified Euler. One is leapfrog, drift kick, drift leapfrog. And the fourth is a standard Runge-Kutta integrator. So again, these two are first order, this is second order, leapfrog is fourth order. And Runge-Kutta has an unfair advantage because it does a lot of function evaluations during one step. So I'm going to choose the step sizes so there's an equal number of evaluations of the force per unit time for each of the integrators, because that's typically the most expensive step in integration. So these are the results. This is fractional energy error as a function of number of orbital periods. You can see that modified Euler up here is terrible. Within 100 or so orbital periods, it's got energy errors that are of order unity. Modified Euler is much better, even though it's still first order. Leapfrog is better than modified Euler. Again, this is the only difference in this is 1/2 step at the beginning and one at the end, but you still get a factor of 30 improvement in the energy error. Runge-Kutta is fourth order, and not surprisingly at the beginning, it does far better than any of the others, but you can see the interesting feature that the energy error in Runge-Kutta is growing linearly with time. That is precisely the property we're trying to guard against by using symplectic integrators. And the really remarkable things to notice is that if you go far beyond 100 orbital periods, even this extremely crude modified Euler will have smaller energy errors than the fourth order Runge-Kutta. The second remarkable thing to notice is that the symplectic integrators don't just reduce the growth of the energy error, they completely eliminate it. That is, you can keep running modified Euler as long as you want. Eventually you'll have some problems with round-off error, but it hasn't just reduced the energy, the growth in the energy error, it's completely removed it. The integration, the energy errors are there, but they're oscillatory and they're completely stable. I should say, of course, that this funny behavior is just because the energy errors in these integrators are oscillatory on a logarithmic scale. I'm taking an absolute value, you can get a spike every time it goes through zero. So this, I think, is a sort of graphic demonstration of why you always want to use a geometric integrator if you're following a planetary system for a very long time.
Scott? So we were told about Hermit integrator yesterday by others. So how does it connect up on this? Where is it?
The Hermit integrator depends on which one you use, but it's similar to Runge-Kutta. It's a integrator which is specifically designed to work well with gravitational n-body systems because the n-body stellar systems that Douglas is dealing with are so chaotic. I think it's fair to say that having a symplectic or geometric integrator is a lot less important there than trying to follow what's actually going on between the stars in the encounters. Now, Douglas, maybe you want to comment on?
No, I was going to ask you the same question.
Okay.
I think that's a clear description.
I'd say that this is a very this is an important question which I could go on about for a long time. I think, for example, if you want to do cosmological simulations, with a cosmological simulation, you're trying to simulate a collisionless stellar system because the collision time in the galaxy is very long. So you don't care about things like forming binaries. And there, I think it's fair to say that people use Leapfrog not so much because it's symplectic, but because it's simple, it has no extra memory requirements, and it's very well behaved, stable, integrated, and they're not trying to do anything all that accurately, so they don't need more than second order. In globular clusters, I mean, it would be a fair question to ask why the people who do n-body simulations of globular clusters prefer to use Hermite rather than Leapfrog. I think the answer is because they really are trying to follow the detailed interactions between the stars, including things like three-body encounters, formation of binaries, and so forth. If you were more cavalier about that, you just sort of wanted to get a pretty good idea of what was going on, you might well be better off with Leapfrog. The second reason is that, as I'll say in a couple of minutes, Leapfrog and these integrators work best when you keep the time step fixed. And so they work very well for systems like planetary systems, where everything's just going around for a billion orbits. Orbits aren't changing very much, there aren't very many close encounters. You're just trying to make sure you can watch very small effects accumulate over a very long time. In globular clusters, you have to vary the time step depending on what's happening to nearby objects, and then the advantages of the symplectic integrators are smaller. A separate and I think quite interesting question is, whether with a different set of people doing globular cluster integrations, they might have actually ended up using Leapfrog and trying to improve Leapfrog rather than trying to develop the best possible non-geometric integrators to follow what's going on.
Well, I think one extra bit there is for the Korean integrator to also try to make the algorithm somewhat time symmetric to get rid of the golden and error.
Yes, that's also correct. I think, are the current Hermites, they're not precisely